Lighting and video, they do visual predictions of what we will see. With audio, we do visual predictions of what we will hear. And that fundamental difference is pretty significant. Does this pretty picture we show and send to the promoters, or somebody sends to us as an audio engineer, represent a good sound or a bad sound? We can see coverage. I mean, it's pretty easy to represent coverage at various frequency responses. But what about audio quality? What does it sound like? Is this subarray a better sounding subarray or a worse one? One of the things about sonic predictions is it really inspires us to weight even coverage over sound quality. We can see that it covers evenly, but does it sound good? When we look at subarrays, they tend to fall into 3 different configurations and a combination of those 3 different configurations. Configuration 1 is a single sub somewhere, like we would have for home hi-fi and the 0.1 systems, where we have low end radiating from a single point in space. And that may be multiple subs or just one. Then we move on to having 1 sub per side in kind of a stereo. We have stereo speakers, we put a sub with each speaker, or the speakers have low frequency content reproduced from them. And the third is delayed arc or lines of sub. We take a row of subs, form a horizontal line array of subwoofers, and they're either at 0 milliseconds or we begin to incrementally increase the time as we reach the outer subs in order to increase the dispersion. So we have the horizontal line, the dual point, and the single point. And there may be multiple points. There may be versions of a dual point with a line in the middle, and various combinations. Those are the basic starting points. Now, each of these types of subarrays have tonal differences. The arrival times of the various subs changes as somebody moves from side to side or closer or farther from the arrays, and this impacts the way that those signals sum together. They'll also have coverage differentials. One subarray may cover very evenly throughout the middle area, but die off very quickly to the sides, which is very common for a line of subs across the center. We may have a large peak in the center and pretty good coverage off to the sides, but big holes on either side of center, which is what we get from 1 sub per side. We may have all of the low end coming from one area and it dying off very quickly everywhere else. We have an even coverage, but maybe a sound is going where we don't want it to, or we don't have a lot of control, which would occur from that single point sub. Making the decision of which of these subarrays and how to prioritize tonal differences, coverage differences, and also efficiency differences. Different subarrays are more or less efficient than others. If you have a bunch of subs all at the exact same time, very close together, that's going to be maximally efficient. If you have a delayed arc setup across the front and you've incrementally increased the delay times, you've increased your coverage off to the side, but you've also reduced the overall efficiency of the system. How drastic is that? How many more subs do you need? How much quieter is it than a sub array that's more efficient? I see that quite a lot. We see these sub arrays that get designed to get a really pretty picture, but then when you compare it back to a simpler array, there's a significant drop in decibel levels that may or may not be acceptable. Maybe we can add more subs to it and get that dB back. Maybe we don't need it, or maybe that drop in level will be the difference between an impactful show and one that's lackluster. If you spent any time hanging out with me or watched a lot of the videos that I'm doing, you may begin to know or realize that I will look at a problem or a challenge for a week, a year, or even decades until I can find a way to solve that or demonstrate it or at least understand it in such a way that I can share it or utilize that understanding to improve my craft. And this is one of those things. I've been touring for a long time, hearing all these various subarrays, looking at sound predictions for subwoofers, breaking it down into third octave increments. I've done videos, other sub-videos on showing how to look at subarrays in narrowband outputs and find out where their coverage patterns vary and trying to improve our arrays that way. And now I've reached another little breakthrough in that thought process. I've figured out a way to demonstrate the difference in sound between various subarrays and various listening positions. And this is what I did. I went into Sound Vision and I identified 4 locations. One location out in front of mix position, maybe 100 feet back, another maybe 30 degrees off axis, another about 60 degrees off axis, and another location on stage. So now we've got these 4 different locations, and in each of those locations in delay finder mode, if you click on the screen, you can see a pop-up that tells you the arrival time of each of the sources. And since I established these 4 subs as separate sources, I can see the arrival time of each of the subs at each of these locations. Then I went ahead and built 7 different subarrays. One subarray with 4 subs evenly spaced across the front. The next one with 4 subs evenly spaced across the front, but the outer 2 delayed 6 milliseconds in order to widen the coverage. The next one I did was 2 subs stacked per side, and then 2 subs per side in an end-fire configuration pointed outward. Then 2 subs per side in a cardioid configuration pointed outward. And then finally those same 2 end-fire and cardioid with the subs farther apart. So here's what I did. I selected a point in space and looked at the arrival time and decibel level of the 4 subwoofers from the evenly spaced arc. Sub number 1 arrived at this decibel level at this time delay. Sub 2 arrived at another decibel level, another time delay, and so on. And I programmed each sub into an individual channel. So those 4 channels represent those 4 subs as heard from that listening position. Then I took channels 1 through 4 and grouped them into subgroup 1. So if I PFL subgroup 1, I can listen to those 4 subs from that listening position. In channels 5 through 8, I programmed in the next subwoofer array configuration from that same listening position. And then the same 9 through 16, another array. So each block of 4 channels is a different subarray. And I did that all the way down for that listening position. Then I saved that scene and then called up a fresh scene and selected a new listening position and then saved all the various subarrays in blocks of 4 to that scene, and then did the next one and then the next one. So I have 4 different scenes, one for each listening position, and in each scene I have blocks of 4 channels for the 7 different subarrays. Each subarray runs to a subgroup. So I can PFL that subgroup and listen to that subarray from that position, and then go to the next PFL and listen to a different subarray from that position, and readily go through and listen to the various subarrays. Very quickly, call up the next scene for another listening position and go right down. Now, we are able to listen to the difference in sound between the various subarrays from standing in that position. This would be very difficult to do live because you would have to set up a lot of subs and move them all around. Here we're able to do it very quickly. Now there are imperfections in that this is an electronic summation rather than an acoustic summation. So it's not softened by the reflections off the ground and other aspects of real life. We know that electronic summations are brutal to signals, whereas acoustic summations are much more forgiving. So this is a worst case scenario. But as far as accuracy is concerned, we've taken and looked at a subarray in prediction software. That prediction software has taken the electronic summations and given us a visual representation. I'm taking that exact same data and creating a sonic representation of it So what we're hearing is the sonic representation of the visual representation that the software is giving us. So those two are in a line, and that visual representation is also brutal unless it's softened by the software, which often they are, but this does give us a foundation. We're actually going to listen to what we're seeing. Now, in order to bring things closer to real world, I've got a XTA crossover here that is set at a low pass of 80 hertz, a 30 hertz high pass, so we can listen to the subwoofer range when we're PFLing. Additionally, we can alter the crossover points such that we run the subarray to 100 hertz or 125. We can look at the differences of where these issues start to come into play, because different subarrays have different frequency responses depending on the distances and timing. And that frequency response changes as we move around. I can show this in sound vision while we're doing it so we can listen to it and look at what we're listening to, which is taking it full circle. We're looking at something, deriving the information in order to hear it, and then looking at what we're hearing, so bringing it back and seeing if that correlates. In the version of Sound Vision that I have, has some extra features opened into it that allows me to get frequency response of each listening position, and we can look at how that compares to Smart, and we can double check it against itself. All right, so let's go ahead and give a listen to the subwoofer arrays. Okay, we're going to start with listening from front of house mix position. I'll turn on the pulse here. And we can see it on Smart. Let me go ahead and save that. And I'm going to go to the next array. This first array we're listening to now is 4 subs evenly spaced. Next one, we're going to go to 4 subs, the exact same configuration with the outer subs delayed 6 milliseconds in order to increase the horizontal dispersion of the array. Here we can hear it's kind of stumbling. We can hear the time delay, the differential in arrival times, and we can see that in Smart. The next one we're going to listen to is 2 subs stacked per side. Just put a couple subs on each side of the stage. Definitely louder than the one with the delayed arc. And that's because all the subs are arriving at about the same time, very close. Now we're going to go to an end fire, 2 per side. So there's 1 sub behind the other sub, and the front sub is waiting for that. And it's a little quieter than the other 2. We lost a little volume because the energy is being pointed outward somewhat. But it's still a tight, clean sound. Let's do that with a cardioid setup. Now here you'll notice in Smart that we lost some low end. It's rolling off a little faster in the low frequency, and we've got a much deeper cancellation at that higher frequency, which is above our crossover point at about 150 cycles, but it is affecting the overall volume, and we're in the center still. Let's go to an end fire where I've moved the subs farther apart, and I've increased the distance between them so there's a better cancellation. And again, we're very similar to the sound of our first setup. And the cardioid version of that far apart. Now this is interesting. We've lost more high frequency, or not as much as we lost with the delayed arc, but we did lose some high frequency, and the cancellation nodes drop down, but we've gained back that volume. All right, so these are, I'll go through them and we'll listen to the 7 different setups. All right, let's go ahead and move over to the next point, listening position, which is about 30 degrees off of axis and kind of the side of mixed position. It's not in the null there, but you can see that in the graphic I'll show. And we'll start with the first set, 4 subs evenly spaced. Now here we can see that we've lost volume, and we know that we lose volume, and we can see that we lose volume in the graphic, in the prediction, and we can see that we have dips in the response, and this is what happens when you're off axis of a very beamy subwoofer array. Let's go on to the delayed arc. You can hear it stumble, boom, boom, the different arrival times of the nearer and the longer and shorter delayed subs, or the non-delayed versus the delayed. Now we're going to go to 2 per side. And here we're off axis, and we can see that we're losing low end. We're getting that cancellation node that we see when we walk across the front. That affects the frequency response. And let's go on to the end fire. Slightly improved, but still we're getting that low end roll off in that area. And we'll go on to the cardioid. Here we have the low end roll off, and we have that dip in the response, and we have even more low end roll off than we had before. And now we'll move the subs out farther to the wide. And we gained back some volume because we have these subarrays farther apart. They're not interfering with each other as much. And we've gained back some of the lows and some volume there. So it's beneficial. And the cardioid with everything far apart. And I'll go back through those. All right, let's go on to listening position number 3. Through these things, we can hear the stumble. We can hear when they're summing all at once, and we get maximum volume, maximum efficiency, and we can hear the stumbles that are giving us some cancellation nodes that are beneficial in reducing levels, but they're also detrimental depending on where we're standing or listening from or measuring from. So we'll go on to the 3rd position here. So now this is that beamy set of 4 space subs, and we're off axis, where a lot of people tend to be. I mean, if you look at those 2 sides, typically 1/3 of your people over here, 1/3 are here, and 1/3 are here. So this is the outer third on either side. So it's 2/3 of your audience tend to be in these areas. So this is typically a very crucial area that often is overlooked. So this is what happens. You bunch of subs in the middle, no time delay. It's number 2. This is with the space delay. It's dropping up, but not quite as bad. We'll go back to number 1. So by putting that delayed arc, we're increasing our coverage in the horizontal. We're gaining a little volume. Let's go ahead and go to number 3, 2 subs per side. And here we're hearing the near subs and the other ones far away. Is that boom, boom, boom. And that's giving us some cancellations, which we see in the response here, and some loss in low end. But we definitely got more volume than we had with the being off axis of a bunch of subs that have a wide horizontal array. And that makes sense. You have a wide array, it's going to be beamy. And you put time delays, you're going to lose efficiency. Let's go to the end fire, narrow end fire. Narrow cardioid. Wide end fire. Go back to the narrow end fire. Because they're not as close together, they're not canceling as much from the far side of stage to the near. Let's go ahead and go to the cardioid wide. And now we're hearing the time delay, that cancellation that we're putting in the cardioid, that polarity reverse to get rid of low end on stage is causing a stumble off axis. Let's go ahead and look at that. And we say that we've got all kinds of interference there. So now what do we got here? We have these varying sounds. Different arrays sound good in different areas. And some sound not that great everywhere, but not too bad anywhere. So ish. And these are some pretty simple arrays. We can do better than this, but it's a good look at it. Let's go ahead and look at our 4th position. Now this is a position on stage. Everything, if you can see on the meters here, everything's very hot now. We're getting a lot of output on stage, especially for some of these arrays. So I'm gonna have to turn down, well, I won't turn it down at first. I'll go ahead and let this thing clip. And well, we can see it there. Let's see what happens. It is clipping. We're not that worried about sound quality of this. This is not really that tonal related as how much energy is this subarray putting on stage. And we can see that it's significant. It is much louder than it is at front of house with the 4 subs across the front. And we'll put that into a delayed arc. We'll time delay those outer subs. We've reduced the low end on stage. We can hear that zipper sound, but that's this is what the subs are doing to the musicians. But it's up in the higher range. Now this peak is up here at 68, 70 cycles. It's probably not going to be near as bad with this delayed arc as it was with just the 4 subs and no delay. So that delay on the outside, it's widening the coverage out front, but it's also widening the coverage on stage, which is distributing it more evenly and not having that big center point. Let's go ahead and put 2 per side. And that's a lot of energy on stage, and it doesn't quite go as low, but it's significant. Again, we're really hitting that stage energy pretty hard. We're going to go with the end fire 2 per side, the narrow end fire. And now we're seeing the cancellation of that end fire array, reducing the amount of energy on stage. We're probably 30, I can see what it is here, 39 to 36, 4 dB, maybe more, plus its narrower band. So this end fire has helped quite a bit. And let's go to the cardioid on stage. That's huge. So that cardioid array had that stumble out front, especially off to the sides, but on stage, it's really beneficial. Now we'll move the arrays out farther. This is an improved end fire array with a larger distance, about 6 feet between, so the cancellation frequency is lower. And we're getting better cancellation there. Let's go ahead and do a cardioid. And the subs are farther apart physically, so they're farther from the center of stage where we're measuring, and that reduction in volume is beneficial. And there's the far apart cardioid. I mean, there's really excellent cancellation on stage. We're seeing 54 dB, almost 20 dB lower than we had with just 2 subs per side stacked. I'll go through that real quick. All right, so there's a quick listen to all of the subs from the various positions with a pulse. I'm going to wrap this up, and I'll do pink noise and actual kick drum in other videos. And leave me comments. Let me know what you think. Let me know what tests you'd like to hear, and see where we want to go with it. Cool. This is fun stuff, and hope you enjoyed it. Let me know. So coming out of this, you should have the information you need to download a free version of Sound Vision and program that into your console of your subarray and put various listening positions out there and see what your subarray in your club, venue, or potential one you want to use sounds like in various listening positions. Very cool. The turning point for me in coming up with this ability to listen to subarrays came from doing Coachella this year. We had an artist on outdoor theater with a great tech and an awesome engineer that was pushing for a very specific subarray. And that subarray, I know from experience, does not sound great, but it does have decent coverage of the front, center, and middle-ish area, and does not have a very good coverage of the off-axis, the 30 to 70, 80 degrees off-axis areas, which are very important. We have like 60% of the people watching the show are in these off-axis areas, and to have that be thin sounding and not a lot of low end, especially for an artist reliant on subs, is less than optimum for the festival. So we went back and forth in trying to do what's best for the festival and keeping the artist happy, which is something that I very much enjoy doing. And as I was going through this process, I really found myself wishing I had a tool to demonstrate what the issues were. Yes, we're looking at these pictures and you can debate whether this color and this many dB is acceptable or unacceptable off axis, and whether the sound of this array will be desirable or undesirable. And I didn't have a good way. I mean, all the software kind of butters over it in a different way and makes it look better than it is. You see the smooth coverage fading off to the side. And what does that actually sound like? I finally came to the realization, wait a minute, I can recreate this. I think I can recreate this. I can reprogram that back into the board. Then I can take the direct signal. I can take a pulse, pink noise, or even a real kick drum and run that into a console, recreate the cancellation, the summation, the sound of that array at this listening position versus the direct signal. Then leave the direct signal the same and move other listening positions. Look at the prediction for the direct signal. Make sure it's not dropping. Maybe the direct signal drops 3 dB off axis. Drop the direct signal off axis. Look at the tonal balance between the main PA and the sub at these various listening points. Not look at them, actually hear them and see if those are acceptable sounds. This could be a very valuable tool. In addition, I do a lot of work with long distance sound propagation and noise issues, mitigating noise issues for festivals. And this is a tool that I believe I can implement to predict or do investigative research as to what caused the issues.